So, what do I want to do? I want to find the current of the inductor for all time. So that means I got to go through step 1, step 2, 3, and 4. So, there you go. So what I'm going to do then is that I'm going to apply KVL and KCL. So I could go in here and I could just say, that works most of the time when I go to look for that x2 variable. But you're going to see in this case, I set it up on purpose to make you aware that it may not be that way. So here we go. So we start with step 1. So I'm looking at KCL. So let's look at KCL. So what I see here is that the switch is now thrown. Right? It's open. If it's open, that means here, I can see that this current's coming in, and what's it doing? It's splitting right there. So I see here that this has to be what? 5 halves, comes in, and then it spreads out. So then it has to be what? IL plus IC. I convert IC. I convert IC because now it has to be what? The cap value times S hat VC. So right away, I see that this whole equation then is what? Determined by IL and VC. That looks good. I'm going after the second one now. Here's KVL. So KVL says I got to connect that voltage and this voltage. Now note, even though I didn't put polarities here, I think we agree that that's the way it has to be. So then this branch here has to equal that branch. So here we go. So this branch, the voltage across this guy, has to be V6 plus VC, and that has to equal V2 plus VL. So when I look at this here, you can see that the guy I got to convert here is that I got this guy, that guy, and that guy that I have to convert. Let's convert them now. What do I know about V6? It's in series with the capacitor, so I'm immediately going to write this as what? 6IC VC, and this guy is in series with the inductor, so I'm going to write 2IL VL. So what I'm seeing here is that I purposely left these to the end here, so now I use the capacitor equation and I use the inductor equation. Let's put them in now. So if I look at IC, it has to be what? 1/8 times S hat VC. So then this tells me here that I'm going to get 6 times 1/8 S hat VC plus VC on this side. Okay? Then I look at the right side, and I look at VL, so the inductor equation tells me it has to be the inductance times S hat IL, so it has to be 2IL plus 2S hat IL. So right now, I have my equation right here. So if I look at this thing here, I'm not going to go matrix this guy up here. Now it looks like I'm wrong in what I said earlier. Because what I said earlier here is that I said that I was going to have 2 equations with S hat IL. I don't. What I have here is I have 2 equations with S hat VC. So that's not, it's incorrect what I said. So now I'm going to matrix this guy up. Okay? So I'm going to put IL to be the first variable. So here I go. So then I'm going to go, so look, I'm going to jump now. I'm going to go from this right into matrix form. Okay? Here we go. So if I do that, this first equation gives me 1. Then I get 1/8 S hat. And I'm going to do IL VC then if I look at my source here is 5 over 2. Now I'm going to look at the second equation. I'm going to keep this positive, and then I'm going to bring all these terms over to the other side. So this is positive right here, so this has to be what? 2 times the quantity 1 plus s hat. So then I'm going to write 2, 1 plus s hat. Okay, now here's my negative sign now. So my negative sign means that I bring this over, so I'm going to get minus the quantity here. So I'm going to get 1 for VC plus, I get 6 over 8, that should be 3/4. So I get 3/4 s hat. What's my source value here? 0. Okay? Now that I have that, now I'm going to go in and I'm going to take the matrix of this term here. I'm solving for IL, which is this column here, so that means the right side of my equation is I replace this guy with that guy right there. So now I'm going to solve for IL. Okay? Here I go. So when I solve for IL, I'm going to do what? I'm going to keep this guy down here, and I'm going to take my matrix now. Okay? I'm going to take this matrix, and when I do my determinant. So remember, positive, negative. So I go 1 times that quantity, so it's going to be 1 plus 3/4 s hat with a minus sign. And then I'm going against the flow, so then I get another minus sign. I get this quantity times that quantity. Look at that. That's 2 over 8, so it should give me a quarter. So I'm going to get a quarter for the constants. And then I'm going to get s hat times 1 plus s hat. And this is all operating on IL. I go to the next part now. What's the right side of the equation? Look what I'm going to do here. I got to take the determinant of what? These are my ILs. So I'm going to take this guy and I'm going to replace it with my IL term. So I get 5/2, 0. And then this guy gives me 1/8 s hat. And then this guy gives me minus quantity 1 plus 3/4 s hat. And it looks like that.
Don't you want term VLT?
I'm not sure what you said.
Never mind, sorry.
Okay, cool. So then I'm going to take the determinant of this thing. Now note, this is an operator equation, and it operates on 5/2. So let's look at this thing here. So if I write this in detail, it's got to look like this. I have to put the 5/2 on the right side, right? An operator has to operate on something. And then you can see that the other term is 0. So now let's look at this thing. Look at that s hat. What is the s hat? It's the derivative. If I take a derivative of a constant, it's 0. So then I get what? Minus 1 times 5/2. So I get minus 5/2. Now I got to clean up this mess. Now note, look at this here. Minus sign, minus sign, minus sign. I'm going to drop all the signs. All the signs are gone now. Okay? So I'm going to do plus here. So when I look at this guy, they're going to disappear now. So now let's multiply this out here. So note, that's a constant. That term and that term right there gives me my what? My first order derivative. So this guy and that guy gives me my first order derivative. You can see my second order derivative is only that term right there. So let's write it out here. So I get a quarter s hat squared, that's these two terms. Then I get this guy. So look what I get here. Oh, dude, this is sweet. Look at that. I get a quarter s hat plus 3/4 s hat gives me 2, right? So then I get s hat, and then I get that one constant here, which is plus 1, operates on IL. So now I'm going to clean up this mess. How do I clean up this mess? I got to isolate s hat squared. right? So I isolate the s hat squared term. So I multiply everything by 4, so I'm going to get what? I'm going to get s hat squared plus 4s hat plus 4 il, and then I multiply this thing by 4, which should give me 10. Here's my equation here. Now note, I'm going to do a check just to see if it makes sense to me. It doesn't mean that it's right, but I want to check this thing. So what do? First thing I'm going to do here is that I'm going to solve for the V constant. And remember, this is the force response. So if I, at steady state, so at t equal to infinity, this tells me that IL should be a constant, which we call V. So here we go. If I plug that down into here, I'm going to get 0 plus 0 plus 4V equals 10. So that means here that the current of the inductor at infinity, at time t equal to infinity, has to be 5/2. Now let's go check with circuit. So if I look at my circuit here, what happens at t infinity? Well, the inductor's open, there's no current. I only have one loop. Look at the current, it's 5/2. So that means here that at IL infinity, it is 5/2, and so these guys check out. Remember, that's not a guarantee that you have the right equations. In fact, some of you guys, I was impressed with some of you people on the first problem on the quiz, because people were not using the technique that I did with I short circuit and all that. They were deriving a differential equation. The problem is that half of you SOBs got the wrong equation, but you got the right P constant. So that kind of screws it up, because then you screwed everything else up. You got to go back and you got to look at that circuit and just say, does this make sense here? Okay? So that being said, let's go to step 2 now. So step 2, we now determine it's a derivative.
Oh, okay.
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 So
here we go. So,
there's going to be 2
look.
videos.
I'm confident in my equation, right? Because I did a check. I don't know if you should be too confident, but let's go. So now that we did this here, we see that now I look at the characteristic equation. So the characteristic equation, it says what? The source term equal to 0. So that means that I get s squared plus 4, s plus 4 equal to 0 right there. Okay? Now if I look at that equation, the first thing that you should do is that, can you look at that thing and see what the solutions to S are? The answer is yes. I can write an equation like this, which means that S1 is equal to S2, which is 2. It tells you that you have identical roots. There's a minus sign, yes. So I have identical roots. If I have identical roots, that immediately implies that now it sets in a whole process where we sort of like just start turning the crank. Remember, there's no physics involved in this thing, right? We're just doing this. I go to critically damp, so what do? I go to the board, I look at the critical damp, and immediately it tells me what? That X critical damp implies that the inductor of T must have a solution of what? E to the minus alpha T, A1 T plus A2 plus the quantity B here. There's no choice in the matter. So, do I know what alpha is? Well, there's a couple things that we can do. You know that alpha So if I look at this, I know that I have this equation that looks like this here. So I could immediately look at this guy right here, and then look at that term right there, and you could see that 2 alpha must equal 4. That tells you that alpha has to be 2. So I'm going to write the general response here. So the general response now is e to the minus 2t, a1t, a2, plus we calculated b already. B is 5/2. So this is what the inductor current is here. That is the general response, right there. So now, the question is this. Let's go calculate A1 and A2. How do I calculate A1 and A2? I got to go calculate the initial conditions. From the initial conditions, I then plug them into this guy here, and I apply them and force A1 and A2 to match those conditions here. So here we go. So now we're at step 3. So now we're going to calculate initial conditions. Here we go. So at t equal to 0 minus, what does my circuit look like? So I have a current of 5/2 amps. So if I go back to my circuit here, you can see that at t equal to 0 minus, I have a short here which kills off that current right there. So if it kills off that current, then this guy becomes a short, that becomes an open here. So if I look at the circuit here, I have and so that means here that I have my inductor current looking like this, and clearly VC at 0 minus must be 0. Why is that 0? Because you can see that that branch and that branch are in parallel, and shorts, of course, have a 0 voltage. So therefore, I see that VC of 0 plus then has to be 0 volts. IL of 0 plus has to be 5/2 amps. So now I got my initial conditions for that. Now what happens is that the switch is thrown, which tells me I'm in the region of 0 plus. So at 0 plus, we already know these guys. What we don't know is we don't know the derivative of the inductor current here. So we need to determine S hat IL at 0 plus. How do I do that? What I go do now is that I go and I look at the 2 first order equations. So the first thing that I look for is that is there an equation 2. So I'm going to come all the way back here. Here's my first 2 order equations. And when you look at these equations here, what am I seeing here? Note that this does not contain the derivative of the inductor. This one does. So therefore, that is equation 2. So now I got to look at that equation right there. Okay? So if I look at equation 2, what does equation 2 look like? So looking at this, look what I got to do. I got to solve for this guy now. So I got to take this guy to the other side here. So if I do that, note that I'm going to get S hat operating on this guy gives me these 2 terms here. It gives me VC plus 3/4 S hat VC minus 2L, 2IL, excuse me, divided by the whole quantity 2 here. Now, one of the things that should bother you a little bit here is that note that I got 1/2. So now if I look at S hat, IL at 0 plus, I'm going to look at this guy. It's going to be plus 3/8 S hat VC of 0 plus minus IL at 0 plus. Do I know what that value is? Yes, right here. Do I know what this value is? Yes. Do I know what that value is? No. And when you look at this guy here, this guy's causing a problem. So what do I got to do? I got to go back to these equations. There's that SOB right there, right? I got to take this equation. For right now, I'm going to call this 1. I got to solve for this guy in order to solve for that over there. So what I'm going to do here is that I got to use both equations to get S hat IL at 0 plus. So if I look at equation 1, you can see that I'm going to solve for VC, S hat VC. So if I look at 0 plus, that guy's going to be what? 5/2 minus that other term, which will be IL at 0 plus, divided by, nope, multiplied by 8. So when I look at this, I have this guy here. So now, let's go calculate these guys. Okay? So for starters here, let's look at this guy. The first guy here is what? VC of 0 plus is 0. So that means that this term right here is gone. So then I get what? 3/8 times S hat, but no, this is S hat VC right here. So I'm going to plug in this term right into there. So then I'm going to get this guy 8 times the quantity 5/2 minus IL. What is IL? 5/2. And then I get this guy here, which is my last term here. So I get minus IL, which is what? 5/2. So all I did here is that I plugged this term right into here. And what you're seeing here is that immediately this sums to 0. So what's my inductor current looking like? So this tells me here that I get S hat IL at 0 plus is minus 5/2 amps per second. So now I got my initial conditions here, right? I got the derivative term. I got my non-derivative term. So what do? I'm going to go to step 4. What does step 4 say? I take these two guys here and I apply it to this equation right here. So I got to move that way. I got to move this way over here. So I'd like to leave this circuit alone over here for right now. So what I want to do then, so now I'm at step 4. Now I need to determine constants A1 and A2. So here I go. So my general response is what? It's IL of t. And then that guy tells me it's e to the minus 2t, quantity A1t plus A2 plus 5/2. Now what do? I apply the initial conditions. So I have to apply initial conditions to IL of t. And that makes it what? Realistic. So here I go. So IL at 0 plus has to equal what? That tells me it's got to be 5 halves. So I'm going to write 5 halves. But now I got to take my 0 and I got to plug it right into here. If I plug it into here, I'm going to get what? E to the 0 times the quantity A1 times 0 plus A2 plus 5 halves. So when I look at this guy, I get what? I get this quantity here gives me what? A2. But look, I got 5 halves on both sides. This immediately tells me then that A2 must be 0. Okay? A2 is 0. So I can immediately come in here and kill off that term. Right? So this comes in here. This guy tells me that this term is gone. So now, what do? I take the derivative of my general response. So now I have S hat IL of 0 plus. So that means then I got to take the derivative of this term here. So it's got to be e to the minus 2t times a1t plus 5 halves. I take the derivative now. So clearly that term is 0, so I won't even think about that guy. It's this guy that I have to pay attention to. So if I pay attention to this guy here, this guy tells me that it has to be what? I got to do minus 2 e to the minus 2t times t plus, the chain rule says that I give this e to the minus 2t times the t gives me that quantity right there where I factored out a1. So then, at t equal to 0 plus, what do I get? That's 1. This whole term goes to 0. Right? Because look at the t right here. Since t is equal to 0, that whole term cancels out. So the only thing I have left is this guy right here. And you can see that at t equal to 0, this guy now equals what? A1. But what is this guy equal to? 5 halves. So therefore, right, what did I get? With the negative, thank you. I got a negative, so now I know what A1 is. Right? I know what A1 is. I have my complete response now. So when I look at that, the complete response is IL of t has to be then what? It's got to be 5 halves minus 5 halves e, let me make sure I get this right, e to the minus 2t t. Right? Which would give me 5 halves 1 minus t e to the minus 2t. Okay, let me check my notes and see if that's what I got. I don't even know what I got. Something different than I know. Let's make sure. This agrees with my notes right here. Okay? That has to be true right here.
Your last row here, you forgot to distribute -2 into it, so it should be -2 e to the negative.
Yeah, but that whole term goes to 0.
Then that's over. I mean, yeah. That,
This guy? But I don't take the derivative of the exponential. I have to use the chain rule to take the derivative of that guy and that guy.
oh, I did the channel. back to it, like distributed over.
I don't know, I'm gonna say that this has to be the solution. It's gotta, if it's not, it's gotta be pretty goddamn close. Okay, because I am not seeing, right? Do I have any errors here in my algebra? Right, did I solve for this guy right? So if I solve for this guy right here, that's 3/4. Yeah, that's 0. That's 3/8 minus IL 2. 5/2 minus IL. Looks good to me. I plug that in, that's 3/8. It's gotta be, I don't see any mistakes. Okay. So let's look at what this means here. So if I was to plot this thing, where is this guy starting at? So I'm going to erase this whole thing right here. So if I was to plot this thing, what am I seeing? So when I look at this guy here, if this switch is closed, what I'm seeing here is that there is less resistance that this inductor is seeing, right? If I include this 2 ohm resistor, there's less resistance that I'm seeing. When this switch closes, what does it do? It sees less resistance relative to its branch. And if it sees less resistance, am I going to get more current here? Should it reduce the current that the inductor sees? I'm going to say that it should increase it. Let's see if there has to be some pulse there. So if I look at this plot here, if I go and I plot IL of t, I'm seeing that initially this guy's coming in at what? This guy right here. Okay? This guy's coming in at 5/2, so that means it's coming in at 5/2. So IL of 0 minus is coming in at 5/2 amps, and then I suddenly get a pulse here. Now, is this consistent with that initial condition? You can see that at t equal to 0, this term is dead, and then I get that. But now you could see, look at this driving term right here. This term is negative. As this thing increases, it increases in the negative direction. So what it means here is that when I look at this line right here, this guy has to then jump exponentially, or it's a function of that, and as it jumps here, I'm expecting that it has to do something like this, and then it decays as quickly as possible back to the 5/2 line. So this tells me here that I at infinity still has to be 5/2 amps. And that's what I mean by critically damped.